Okay, in this last one, I want to spend some time going through all of the steps involved here, and do it quite carefully. Yeah. So let's do that. Um, and then we'll summarize at the end, maybe with sort of general comments about what the solution kind of looks like. Okay. Uh, yeah, let's go through an example quite meticulously. So the example that I want to do is the following initial value problem. And I'm grabbing this straight from the book. So we have 2y double prime plus y prime plus y equals 0. And we have the initial values of y of 0 being equal to 1 and y prime of 0 being equal to negative 2. Okay? Now, the general approach to solving an initial value problem like this is to first solve the differential equation and then use the initial conditions to figure out the unknown constants. Okay, so that's what we're going to do. Now, this differential equation here differs from what we've seen in the past because the coefficient in front of y double prime is not 0. Um, but all of the logic that we've described works in this situation just as well. If we didn't have just as well. I mean, what we could do, of course, to get it into a state where it's uh, uh, like in compliance with what we had in the past, is simply divide this equation by 2 everywhere. In which case we would get y double prime plus 1 half y prime plus 1 half y equals 0. And that's fine. And you could go ahead and solve the problem that way. So if that makes you comfortable, cool. But you could also just as well, and I'm not going to do this because I'd rather not deal with too many fractions. I don't think it all ends up working out the same, but I'd rather just not deal with fractions right now. I want to put that off until later in life because maybe I get hit by a bus and like maybe a bus comes diving through that window and I get crushed by it and then I don't have to work with the fractions. You know what I mean? So I'm going to put that off into the future and instead just attack this differential equation as is written. The characteristic polynomial in this case, we're operating under the same guess that y is equal to e to the rx. The characteristic polynomial in this case is 2r squared plus r plus 1 equals 0. Okay? And now we're going to use the quadratic formula to try to figure out what r is. So r here is going to be negative 1 plus or minus the square root of b squared, which is 1, minus 4 times a times c. So 4 times 2 times 1. 4 times 2 times 1 is 8. Oh, God. And then this is divided by 2. 2 times 2, which is 4. Okay? This is not pretty, but it is what it is. Oh, my God. What have I done? Go away, everything. Oh, my goodness. Okay, there we go. Okay? Should use the eraser tool. Erase. Okay. It still looks hideously ugly to me. So this is negative 1 plus or minus the square root of negative 7. Oh my God. Divided by 4. And then this is negative 1/4 plus or minus square root of 7 over 4 times I. Okay? Right? Square root of negative 7 is, you can think of it as square root of 7 times the square root of negative 1. The square root of negative 1 is I. Just relax, okay? Formalists out there. Yeah, so we have this here. This is a pair of complex conjugate roots you will not be surprised to find. And we need to consider only one of the solutions, that the one of the complex valued solutions. So here is a complex valued solution. I'll write it in purple. It's given by y equals exp of negative 1/4 plus, let's just take the plus 1. I could take the minus 1, but I'm just going to take the plus 1. Square root of 7 over 4 times I. Okay? And what we have to do is find the real and imaginary parts of this complex valued solution. Okay. Oh, I'm sorry. I messed up. Oh my God, I messed up. This is this is not a solution. This is just a constant right now. Okay. In order to make it a solution, I need a function here. So let me put parentheses there and put an x in front. Okay, much better now. Yeah, you see the problem? Okay, hopefully you saw the issue. Okay, now what's the trick here? Because this is a different situation than what we had in the previous problem. In the previous problem, our root of our characteristic polynomial had no real part. It was purely imaginary. That is no longer the case. Here we have a non-zero real part. It's negative 1/4. So what do? Curl up in a ball and die in that corner right over there? Looks very cozy, but no, let's not do that. Let's instead use a combination of rules of exponents and Euler's identity. It's always helpful to write Euler's identity. I like Euler's identity. Highly arousing. Here it is. It's e to the I theta is equal to cosine theta plus I sine theta. Have I mentioned that you should have this tattooed on your brain somewhere? Don't get any ideas. This is okay. Anyway, complex valued solution. Yeah, we're going to invoke Euler's identity here. So how? We're first going to distribute this x here. We'll distribute this x like this, here and then here, okay? So if I do this, what I get is x of negative 1/4 x plus, no, oh my goodness, times x of square root of 7 over 4 times I times x. Because remember, exp of a sum is the product of exponentials. Exponential of a sum, exponential of a plus b, is the product of exponentials. X e to the a times e to the b. So that's what's happening here. Okay? Now, this part right here is just some real function, real value function. We know it. It's a decaying exponential, right? So that's cool. This part right here is truly complex. And for that one, we want to break it down into its real and complex parts using Euler's identity. Okay, so that's what we're going to do. We're going to rewrite this as, I'm in red now. Let's make blue. Blue. We're going to have exp of negative 1/4 x out front. And then I'll put a big old bracket. Because now what I'm going to do is rewrite this part right here in terms of cosine and sine. I'm going to play that same trick. What's playing the role of theta here? Here, what's playing the role of theta is square root of 7 over 4 times x. If you make theta be square root of 7 over 4 times x, then this, oh my God, this underlined in blue, this thing underlined in red now, is exactly the left-hand side of Euler's identity. So we can rewrite it as the right-hand side. And what we obtain is cosine square root of 7 over 4 times x. You following me? You can't answer. Plus I times sine square root of 7 over 4 times x. Is that clear? You can't answer. Okay, now what are the real and imaginary parts? Well, to answer this fully, what we need to do is one last move. We should distribute this decaying exponential term right out here. We should distribute this like this. Right? Like that. And if we do that, let me just do it. All right. I don't know why, but I want to write it as in the traditional way. E to the negative 1/4 x just deal with it, okay? Cosine of square root of 7 over 4 times x plus I times e to the negative 1/4 x times sine of square root of 7 over 4 times x. Okay? And here is the real part. What did we call it? We called it y. This is the real part of y. And here is the imaginary part of y. Wow, cool. Okay? And so, from this, we can write down the general solution. The general solution is simply a superposition of these two bits. It's given by, I'm just going to call it y. Can you just leave me alone? Okay, maybe I'll call this one y sub, I'm just going to reuse it, okay? The letter y, I'm just going to reuse it. It's y is equal to c1 e to the negative 1/4 x times cosine of square root of 7 over 4 times x plus whole point, I'm sorry, I don't know why I did that. C2 times e to the negative 1/4 x times sine of square root of 7 over 4 times x. That's it. I took an arbitrary superposition of the real part of this complex value solution and the imaginary part of this complex value solution, and I got my general solution. Now, I'm not done. Why? Because don't forget, we have initial conditions here, which I'm going to duplicate and move down here for my good reference. Uh-oh, I carried some other stuff with it. That's okay. I can erase. Okay? So what I need to do now is use the initial conditions to pin down the values of C1 and C2, right? Right now, for any values of C1 and C2 that I shove in there, I'm going to get a solution to this differential equation. That's cool, but I don't want just any old solution. I want ones which satisfy these specifications which I've been given. Okay? So let's use the first differential equation first. Let's do this in blue. So 1 is equal to y of 0, right? And if I stick 0 into here, notice, I'm just going to sort of say it instead of trying to write it all out because it's a lot to write. Notice that this term here, this e to the negative 1/4 x becomes 1. E to the 0 is 1. This term here also is 1. Okay, neat. This thing here is 1. But very lovely, this thing dies, okay? So we don't, all we have left in the end is C1. Is C1. So we now know the identity of C1. C1 must be 1, and that's by virtue of that first initial condition. Cool. How about the second initial condition? 1 is equal to y prime of 0. What? Hello? Negative 2 is equal to y prime of 0. Well, what is y prime? That might be good to know. Really? Are you serious right now? You're going to make me do y prime? Okay, I'm 48. This feels like abuse. I'm an old man. This feels like you're abusing an old man. Okay, all right. No. We're going to persevere, okay? Sometimes calculations get long. And this is just a fact of life. And we're going to do it. Okay, I'm noticing, though, one shortcut that I can take is instead of doing product rule twice, which you would have to do if you had this term and you differentiated each separately, is I can factor out an e to the negative 1/4. And then only have to do product rule once. Do you see what I'm saying? So that's what I'm going to do, just to keep things humane. So y is also equal to, e to the negative 1/4 x times c1 cosine. Oh, and by the way, c1 we now know is 1, so maybe I won't even write that. It's just cosine of square root of 7 over 4 times x plus c2 times sine of square root of 7 over 4 times x. Remember, again, the c1's not missing. It's equal to 1, so I just left it out. Okay, now I'm going to take a derivative, and I'm only going to have to product rule once. So y prime now. So, oh God. I take the derivative of the first chunk, and I get negative 1/4 e to the negative 1/4 x, yeah? And then the rest of it is the same. And you know what I'm going to do to make my life even easier? And this is going to be confusing because it's going to look weird with some of the constants that are involved. I'm going to write cosine as c and sine as s. This is very common. And actually, maybe I've even seen, and I've not used this really in my life, but I feel the need to do it right now. Oh wait, am I going to know how to take a derivative of this? Well, like, I mean, we can work it out, can't we? I'm going to, I wish I had some space here. Okay, not now. Just relax. So I'm trying to be too clever, okay? Let me just shorten cosine to c and sine to s, okay? That's enough cleverness for today. C of square root of 7 over 4 times x plus c2s square root of 7 over 4 times x. Okay, so that's the first chunk of the product rule. But then we have a second chunk, which is e to the negative 1/4 x, so that's the first piece left alone, times the derivative of what's inside the brackets in blue. That's square root of 7 times 4 with a negative sign, sine of square root of 7 over 4 times x, plus square root of 7 over 4 times c2 of cosine square root of 7 over 4 times x. Okay, that wasn't so bad. Right? Okay, but that gives me y prime. And now what I have to do is plug 0 into there. Okay? So what happens when I plug 0 into there? This whole thing here becomes negative 1/4. Okay? Negative 1/4. This becomes 1. And this becomes 0. So I believe that this whole top line of y prime, when I plug in 0, is equal to negative 1/4. Okay? And what about the bottom line? This becomes 1. Oh, God. This becomes 1. This becomes 0. Sine of 0, 0. And this becomes square root of 7 over 4 times c2. Okay. All right. And now we can solve for c2. Do you agree? I can add 1/4 to both sides. Hey, do you know what negative 2 is? It's negative 8/4. Whose idea was it to do this problem anyway? It's negative 8/4. So if we add 1/4 to both sides, we get negative 7/4 is equal to square root of 7 over 4 times c2. Can multiply both sides by 4. So I get that negative 7 is equal to square root of 7 times c2. And then I can divide both sides by the square root of 7. Now listen, 7 is square root of 7 times square root of 7. So 7 over the square root of 7, I know you're going to ask. 7 over the square root of 7, you know what that's equal to? The square root of 7. Why? Because 7 is the square root of 7 times the square root of 7. That's why. Think. Is it clicky? Clicking sounds? Okay. So then this allows me to solve for C2. C2 is negative square root of 7. Wow. Okay, nice. In other words, I've got C1, and now I've got C2. And this is just scratch work, okay? Oh God, I just did something really bad. Okay, there we go. And now we can write down the particular solution, the solution to the IVP. I'll do this in, what's a good color? How about green? I need a darker green, don't I? Hold on. Can I get a darker green going? Maybe this one? Solution to the IVP. It's easier to read a darker green, right? It's given by y equals. Okay, so I'm going to plug these C1 and C2 back into my general solution. So I get y equals e to the negative 1/4 x times cosine of square root of 7 over 4 times x minus square root of 7 times e to the 1/4 negative 1/4 x times sine of square root of 7 over 4 times x. And this is the solution to my initial value problem. Now, if you take the broad view here, really everything in this problem was downstream of this calculation right here, of where we found r. This allowed us to find the real part of the root and the imaginary part of the root, okay? So here's what we can say sort of in general, if we wanted to say something general. So this is what happens when you have a second order homogeneous linear differential equation with constant coefficients. The complex roots case. So if, let's say a plus bi is a non-real complex root of the characteristic polynomial, for the equation y double prime plus p y prime plus q equals 0, qy equals 0, then the solution is given by the following. So we just sort of pattern match. It's going to be given by C1 e to the ax, the real part of this complex number. I guess I need to specify. A and b here are real numbers, okay? Times cosine of bx, okay? Plus C2 times e to the ax sine bx. This thing here is the general solution. All right? And if you're a memorizer, you can memorize this. But if you are a mere mortal, such as myself, without the ability to memorize such things, this is really the process that you follow, okay? I will never be able to memorize this black box here, but I can memorize Euler's identity because I have it tattooed on the inside of my eyeballs, so I always see it. It's always somewhere in my field of view, okay? It's also automatic inside of my hand bones, right? So that's a good place to put it too. All right, this is enough. We will work more with this, particularly in the context of what are called harmonic oscillators. Because if you think about what's happening here, and this is very useful to think about, these solutions correspond to what are called damped harmonic oscillators, where you have an oscillation, but where the amplitude of that oscillation gets smaller and smaller as x gets larger and larger. And as you can imagine, this is a very useful gadget to have for modeling physical phenomena. Okay, that's more than enough. Okay, so long.